Professor Yoshikazu Giga. He is the world-leading expert in mathematical analysis of PDEs, as we all know. He made fundamental contributions in analysis of blow-up phenomena of nonlinear PDEs, Navier-Stokes equations, surface evolution by the curvature and the viscosity solutions. Professor Giga received his PhD from University of Tokyo, and in 1986, he joined Hokkaido University as a faculty member, and after having various positions at various places, including Courant Institute. And then from 2004 until now, he has been a professor at the University of Tokyo. Professor Giga received various prizes, including Nissan Science Prize, Autumn Prize by the Mathematical Society of Japan, and the prestigious the Medal of Honor with the Purple Ribbon by Japanese government. He is an editor of many journals, including Math Analyst and the Calculus of Variation in PDEs. Let's welcome Professor Giga. Yeah, please.
Thank you very much. Thank you very much for your kind introduction and invitation. I'd like to share the screen. It is my pleasure to be the speaker of this meeting. So can I share the screen? Yes, this one. Oh, is it okay?
Yes, it should be okay.
I don't.
Okay. You can share. I don't know. You have to click on share and then on your screen, and then it should be possible.
Sure. Just a second. Okay. Do you see?
Yeah.
Okay.
Yeah.
Now it's.
I can see it now. Yes.
It's fine. Okay. Now Okay. Today I'm going to talk on an overview, give an overview of total variation flow type equations, which tend to be a typical non-local problem. Although the equation does not have any fractional power operators. The plan of my talk, so I'll show you the next slide, is as follows. After introducing several aspects of total variation flow, we explain two important approaches, variational and viscosity approach. And as an application of viscosity approach, I'll give crystalline analysis on crystalline mean curvature flow, which is quite important in material science. Okay. So what is the total variation flow? Okay, in a strict sense, the equation looks like this type of equation. This is the du dt, this is the equation. And of course, it is interpreted as a gradient flow of the total variation energy, where omega is some domain in Rn or Riemann manifold. So this is a very classical total variation flow. But you see, this is another flow, which is often analyzed is a gradient flow of p-Dirichlet energy. So this is something like if you take energy is taken by this way, then this gradient flow in L2 norm is in du dt is divergence. So this is p heat equation. Okay, and of course, if p is equal to 2, it is nothing but the heat equation. But if p is equal to 1, this is exactly total variation flow. So from the point of p-Dirichlet energy, this corresponds to 1 Dirichlet energy. So, but there's a lot of difference between p-diffusion equation, which I should say p-diffusion equation. This is the equation is as I wrote here. And if p is greater than 2, parabolicity degenerates. So if p is greater than 2, this is the degenerate equation at gradient u is equal to 0. And if p is in between 1 and 2, parabolicity is so strong, it's singular at gradient u is equal to 0. Means the diffusion coefficient becomes infinite at the gradient u is equal to 0. And if p is equal to 1, this is called total variation flow, but parabolicity is similar at gradient u is equal to 0. This is similar to the case p less than 2. But also we notice parabolicity is degenerate in the direction of gradient u. So this is different from above. And of course, there's huge literature to study this type of problem. And but they are less, but still there's some many literature for this type of flow. Okay. And let's see, but to go to the further problem, let's consider a very simple example. This is one-dimensional example. One-dimensional example is just du dt is equal to this signature function, something like this function. Very simple, right? Of course, if the one-dimensional case, this is a signature function ux and dx. This is a very innocent look like equation. Formally, this equation ut u sub t is minus 2 times delta of uxx. So diffusion coefficient just delta. But you see, it's hard to give a meaning of this each term because you cannot pull back measure. So this is not well-defined quantity. And this is diffusion effect is so strong at gradient is equal to 0, while it is 0 at ux, not 0. So heuristically, this looks, this gives some impression of this equation. However, this quantity has no meaning at all. But this means the definition of a solution is non-trivial. Of course, it's maybe trivial for most of the audience here, but what I mean is the definition of a solution is not trivial, at least undergraduate people, by undergraduate students, right? So let's see, how do we understand this equation? Speed of the place where ux equals 0. What is the speed of the place where gradient is equal to 0? The question, how does it, for example, how does the profile in the figure move? So suppose that your profile function is something, this everything one dimensional, consider such kind of function. And this part is a flat part. This part is flat part, constant. And what is the motion if you start with initial data like this? Or if how do you think this, how should we move this type of shape? Here's the ansatz. Flat part, which we will say facet, does not split nor bend so that the time derivative of u is constant on the facet. So this moved as keeping this shape. So we assume this stuff. Then, okay, first of all, integrated of this equation from a minus epsilon to b plus epsilon, you get, okay, this is just a simple analysis. Fundamental theory of analysis says this is signature function ux, b plus epsilon minus signature a minus epsilon. And here in this particular picture, the slope slope left of A is +1, while slope right from B is -1, right? Is a negative, so this is -1. So totally, this is -2. Okay. Then, if you assume this ansatz, the speed is constant on this interval, so that the left-hand side is just u sub t times b minus a, right? As epsilon tends to t. So that's our equation. Previous equation is equal to u sub t minus b minus a is equal to -1 minus +1. Okay. Of course, this is just u sub t is equal to -2 over b minus a. And of course, we need a sign here. But this is a b minus a is a facet length, right? Flat part, the length of flat part. What is -2? Minus is minus, because this is in some sense concave, so this should be minus. But the 2 is actually the number of endpoints. And this quantity is called, this quantity is first of all non-local quantity. So that's the reason I would like to say this equation non-local equation, because speed is determined by the facet length. This facet length is of course non-local quantity, and actually this quotient, this quantity is often called Giga's ratio. Of course, this looks like trivial, but in higher dimensional case, I show you, as I show you, this is a very important quantity, it turned out. So the question, is that this ansatz is okay from approximation. This means that the ansatz follow from approximation. That means if you consider such kind of equation, U sub t is equal to derivative signature of ux. If you ask analysts to analyze this problem, usually we modify by signature function and plus, for example, epsilon uxx, so that this becomes uniformly parabolic. Then question, you get the approximate solution. The question, it is quite natural to guess this limit is a solution of our original problem. And the situation following: if the space dimension is just one, then this ansatz follows from approximation, such approximation. But if the higher dimension, it is in general no. So this is you cannot assume such kind of ansatz for n is greater than or equal to 2 if you assume this solution is obtained by approximation. And I warn you, if the driving force, if there's a driving force like this, then the value dx depends on g. This is another very interesting point. Usually such value does not depend upon other term, but in our problem, this does depend upon g. Otherwise, there's no solution satisfying comparison principle. This is second order parabolic problem. So it is expected to have some comparison principle, or yeah. But if you assign this value as the Giga's ratio, there may not exist a solution satisfying comparison principle. Okay. And this is example. Suppose G is something like a positive function, non-negative function, having support in this interval. So G is something like that. The equation is something like ut minus signature ux x plus g. This is the equation. Okay, we take L is equal to 1 over maximum value of g. Then consider zero initial data. Then there are no solution satisfying comparison principle. This is actually explicitly written in our recent paper with Norbert Požár, and it is just published, as Dr. Holland said, Spring and Nature partial differential equation applied 2020 in this volume. I don't know how to understand, but number 39 paper, I don't know. But I done this, this was printed maybe last week. But anyhow, why such a crazy thing happens? The ideal proof is not so difficult, because consider such kind of solution VA, and this is slope A. And VA is actually sub-solution because speed here is, if you assign this 2L, this is a Giga ratio plus. So ut is just standing, this standing. VA is a standing solution, standing function, time independent function plus G. And if L is taken in this way, then this must be always negative. So if you, this is at least sub-solution. VA is sub-solution. So so the solution U is equal to 0. U is equal to 0 it's not so difficult to say this is U is equal to 0 is super solution because compared from below. So the only choice, if the system satisfies comparison principle, it must be bigger than all sub-solutions. So The only possibility is the solution must be U is equal to 0, but it is not difficult to see U identical 0 is not the solution. So you cannot assign such kind of is not necessarily Giga ratio. So this quantity depends upon environment dependent quantity. This I would like to point out. So now let's you see the difficulty of the problem. So what is the examples? There are of course various examples of this problem. First of all, from the theory of crystal growth, there is something like crystalline mean curvature flow equation. This is not one special example of such total variation flow, but point is this non-divergence type. You have extra term. This extra term may have a problem. And another one is this fourth order, and this is coming from relaxation. In this example, U is a height function of crystal on the substrate. This is proposed by Spohn a long time ago. And here's a little bit confusing example, similar to this one, but you have this one, gradient, mode gradient. This looks like total variation flow, but this is not called total variation flow. This is a level set mean curvature flow equation. Because each level set moves by its mean curvature, which was studied by Chen a long time ago, and Goto and myself advanced book independently. This is related to weak general solution of mean curvature flow equation, which will actually explain later. And the important thing is the singularity here is weaker than this one because of this one, right? If the gradient U tends to 0, the diffusion coefficient tends to infinity here, but this is not because of this multiplier. And another example is one harmonic map flow equation. This is the total variation flow whose value is NS2. And this such kind of equation is proposed by Tan and Shapiro and Caceres long time ago. This is a color image. It's a removing noise from chromaticity. And it is a gradient from total variation flow with gradient flow total with manifold constraint of S2. Okay, this is the image noisy. So there are many examples, and each topic studied extensively in recent 10 years, I think, maybe let's say recent 20 years. So I do not give any references at all because of time restriction. And that, okay, but I should say that at least two approaches to attack this problem. And the first one is if the equation has a divergence structure, the theory of maximum monotone operator works well. And the advantage is it applies to higher order equation, including example 2, fourth order problem. This advantage is, of course, it needs some divergence structure, so does not apply the first problem and third problem. And here's the typical theory, classical theory, initiated by Komura and extensively studied by Brezis and others. And the simple, the theory is the conclusion of the theory is very simple. Suppose that H is a real Hilbert space, it's abstract theory. Let E be a convex lower semi-continuous energy, which is, of course, not identical equal to infinity. Then there is a unique solution, U of gradient flow equation. Okay. And moreover, U is right differentiable for all t, and the right derivative equals to the canonical restriction of subdifferential. What is strong? Okay, this is subdifferential, which I will explain later soon. But what is very interesting, and this equation looks like very ambiguous. However, solution knows how to evolve. And the initial data we say is U0 is I don't know where it is. Initial data is taken in this Hilbert space. Yeah, this is in Hilbert space. Yeah, initial data for any Hilbert space. And this is, in many cases, this is equal to the closure of this energy, the domain of energy. And what is subdifferential? Subdifferential is something like subgradient, we say. Each element is subgradient, and if this is a slope of the function touching from below at u, right? And this is the totality subdifferential operator. Its element is called subgradient. If E is differentiable, of course, subdifferential is a singleton. But if Ex is something mod X, and in the product you use a Hilbert space, then this is something like signature function. But this is all value here. This is multi-valued. And this subdifferential is actually maximum monotone operator if U is convex and lower semi-continuous. And this canonical restriction is minimal section, which is called minimal section. This is the smallest F belongs to subdifferential. So as the set of subdifferential is convex set, and in Hilbert space, this is the closest element. This is called canonical restriction or minimal section. This is key content. And okay, what is the definition? How to apply this theory to our total variation problem? This is not so difficult. And to avoid boundary condition, boundary difficulties, we only consider the periodic boundary condition. Okay, let EU is the total variation energy. So this is BV, total bounded variation function, and HDL to Hilbert space, or maybe different sometimes. And if the value is if outside BV, U is the value is infinity. And if E is lower semi-continuous, if H02, this is lower semi-continuous in H. And it is also lower semi-continuous in another Hilbert space, which is less regular, something like H minus 1 space. To simplify the issue, we take average zero function, but this is H1 average zero, but it's dual, the H minus average zero function. And this is EU is of course still lower semi-continuous. Of course, convexity is trivial, but lower semi-continuous is non-trivial. For example, if you replace BV by W1, Sobolev space W11, then this E is no longer lower semi-continuous. Right. So we have to be a little bit careful. So not like this W11, but we have to take BV. So bounded space of bounded variation, which I do not define because we don't use it. But it's bigger than W11 space, having discontinuous function. So having it's a space contains jump discontinuity. And second order problem, if you consider second order problem, we take Hilbert space L2 and E is E, just E. So the fourth order problem, we take H minus 1 average. Okay, and this applying this Komura-Blaise-Pazzi lemma, we get unique solvability. There exists unique global in time solution DTU with initial data U0 in H, L2 or H minus 1 average. And this is applied for fourth order problem by Bob Cohen and myself long time ago. And also fractional total variation flow is considered by Howard and Matson more recently. But anyhow, we can apply that kind of theory. So far it's very classical. And in general, it's different calculated subdifferential. For total variation flow with respect to L2, it is well studied. And I just point out a book by Andrew Bio, Caceres, Matson. This is a very nice book. And it's well studied for subdifferential. But if you use this type of result, we can characterize subdifferential. For example, suppose that U is a set that Ux is equal to minimum value. So with a smooth bound, suppose U has smooth boundary, then the value of subdifferential U is a minus divergence Z. So this is as usual, but these formally looks like du over gradient du. But of course, this is may not be defined in this place. So it turned out this is a Z less than 1 because this is always less than 1. And also we need some boundary condition. We get some boundary condition where nu is autonormal, provided that u is domain of subdifferential. And so this is a graph of u. So this is actually u, sorry. Right? And this is a graph of u. And this is and the value of minimal section. This is the closest element u is obtained by solving obstacle problem. So this is the L2 norm of this element. So minimize, but there's constraint. This and also boundary condition. If Z0 is a minimizer of this problem, then the subdifferential of u, that u is value d minus d divergence Z0. This is uniquely determined. Divergence Z0 is constant. So this is if divergence Z0 is taken constant, is equal to constant, this is we use ansatz. So no facet spring nor bending occurs if divergence Z0 is constant. So this is important for minimal section on facet. And we say a set U is calibrable if there is a vector field and boundary condition. And I don't go to the very detail, but I would like to say one-dimensional interval is all one-dimensional interval calibrable. And all ball is calibrable, but ellipsoid may not be calibrable if eccentricity is large. And there's, of course, various characterizations now available in calibrability. And okay, and now go back, forget about calibrability. And suppose Z0 is a minimizer of the problem P. We set lambda U as a divergence Z0. Z0 is minimizer. And this is called non-local curvature of the graph of U. This looks like second derivative, so we have the comparison principle. If omega 1 is in this way, then we have such kind of comparison principle. And ideal proof is it's not so difficult because this subdifferential is approximated by solving this kind of resolvent equation. So comparison, this equation is of course elliptic equation. You approximate this E epsilon to get the usual smooth elliptic problem, and the comparison principle holds. So the ordering of U is preserved for V. So this is not so difficult to prove. So comparison of lambda is reduced to the maximal principle. But important thing is this this curvature like quantity, curvature quantity is bigger than this corresponding omega 1 is bigger than omega 2. And of course, if U is calibrable, then this non-local curvature is just a Giga ratio. This is actually Giga ratio. The proof is very simple. You take divergence Z0 and integrate against U, then the integration by parts or Gauss formula, Gauss theorem, it's equal to Z0 not nu, but since this is equal to 1 by boundary condition, this is just area. And the left-hand side is, of course, lambda times volume of U, so you get Giga's ratio here, if U is calibrable. And if there is extra forcing term, then we have to set energy like this, having extra term. Everything is fine, but the point is, of course, this energy, subdifferential energy, is, as you expected, it's just subdifferential E. Subdifferential EG is equal to subdifferential E plus G. However, if you take canonical restriction, this is no longer true. This is may not equal. So this is a way we find that the Giga quotient, Giga ratio cannot be used for under non-uniform driving force, even if one-dimensional case. Okay, and non-local quantity here is you have to minimize this quantity now under the boundary condition. And note that this is quantity. This one. Comparison principle for lambda g is, of course, still holds. Okay, now we are going to the viscosity approach. Theory based on maximum principle. And of course, advantage is no divergent structure necessary, but problem is applies only to second order problem so far. Viscosity theory. For any U0, there exists a unique. So our theorem is the following. For any, now it's not the L2, that everything is based on the maximum principle. So this is just for C. There is a unique global in time solution, continuous, satisfying this equation in viscosity sense. Here, F is continuous and non-increasing the last variable. So that problem with degenerate parabolic, an example includes this one. Of course, we have to clarify what does it mean solution. So we have to introduce a notion of viscosity solution. The standard definition of elliptic problem is as follows. A function U is continuous. The viscosity solution, the viscosity subsolution of this equation F equation, if test function satisfying this type of inequality whenever U and phi takes maximum at x hat. So if it's better to write a picture, this is the graph of U, and if you touch phi, then the maximum point is attained in this x hat. So suppose phi and x hat has such kind of property, then you ask differential inequality, this one at x. And super solution is defined similar way. You have to define this way, and you have to declare this mean. Then you get a super solution. This is completely based on maximum principle definition, completely based on maximum principle. And then if both sub and super solution, then this is called viscosity subsolution. This is a fundamental notion of viscosity solution. And we have to define suitable, the idea of definition of viscosity subsolution is following. We have to take suitable class of test function so that non-local curvature for facet is defined. So that lambda phi is equal to something like this quantity. So then a function U is subsolution viscosity subsolution for our problem if phi x hat t has satisfied such kind of expected property when U and phi is something like that. And we did not clarify this one, but this one is you see from our previous slides, something like sometimes it's a Giga ratio, or maybe it's a minimizer of subdifferential. So I do not want to write any details, but if U is a subsolution and V is a super solution, you have a comparison principle. And I hesitate to show the idea of proof even. That's the standard way with a doubling variable, but we have to use some flattening argument, which was applied for a long time ago for the one-dimensional problem, and to compare value of lambda quite easily. And then we use comparison of non-local curvature, but we have to approximate very general facet by facet with smoother boundaries so that non-local curvature is well defined. So this is a fundamental idea of the paper. Okay. Okay, and now we are going to our main stage, crystalline mean curvature flow. So let gamma t be an evolving hypersurface in Rn. The mean curvature flow equation is as the equation many people knows. This is a equation for gamma t. And gamma t, the v is the normal velocity, and the normal velocity equals to the mean curvature of the surface. And of course, the source of this problem goes back to material science, due to Marin's 1956. And this is proposed by to model motion of grain boundaries in annealing metals. And the point is, this equation, if you move the surface in this equation, hypersurface in this equation, the solution may develop singularity, and this is shown by Grayson. Heuristically, it is easy to understand. This is the dumbbell with thin neck. That you see the mean curvature here is very big, inward mean curvature, right? This is not so big, small, but this mean curve. Then before this both sides collapse, this place collapses very quickly, and this actually happens as shown by Grayson long time ago. Okay, and there's a couple of approach, and variational approach is by Braque. So how to extend the solution after singularity. Variational approach introduced by Braque in 1972, but it was extended by Ilmanen and recently by Tonegawa and others. And its original Braque's article is very difficult to read, but now it is accessible due to the work of Tonegawa and others. And this is kind of variational approach. And then there's another approach called level set method. This is by Chen and Goto and myself, and Evanson's book long time ago. I have also a book. And the theory encountered with viscosity solution. This is the first time to meet mean curvature flow to the viscosity theory. And there's even deterministic game interpretation by Cornell Selfati 2006. But anyhow, this is a very important notion to extend, to track the evolution after it creates a singularity, it develops singularity. So, is it possible, the natural question, is it possible to extend the level set approach to an anisotropic curvature flow? This is the answer is already included in my earlier paper with Goto and Chen, provided that interface energy density is convex and smooth. What happens interface energy is not C1, strong anisotropy. So this is the case of crystalline mean curvature. And crystalline mean curvature for a typical example anisotropic mean curvature for which, for example, describe a motion of anti-phase grain boundary. And anisotropic mean curvature is a change ratio of an interface energy with respect to variation of volume enclosed by hypersurface gamma. So this is a change of ratio of not the surface area, but interface energy, which I'll explain. So, and interface energy, that gamma zero, this is given depending upon materials, negative non-negative continuous function over the unit sphere, which is called interface energy density. But a given hypersurface, we said I of gamma this is the interface energy, which is called interface energy. The N is, of course, normal of gamma. Anisotropic curvature flow is introduced anisotropic mean curvature. So this is anisotropic mean curvature, and it is explicitly written by using minus the surface divergence gamma xi n, and xi is a gamma gradient of gamma. Gamma is a homogeneous extension of gamma zero. And divergence gamma is denoted by surface divergence. The vector field is often called Kahn-Hoffman vector field. But anyhow, in the case of anisotropic case, if gamma 0 is equal to 1, in the case gamma 0 is equal to 1, this is nothing but usual mean curvature. And the notion of roof shape is quite important. And this is a substitute of sphere. And this is something like roof shape defined in using this gamma and m, and yeah, and you have to have such kind of stuff. Then the weighted mean curvature n is equal to a constant. The converse is also true. This is Alexandrov anisotropic version of Alexandrov problem. If gamma is compact and embedded, and gamma zero smooth and strictly convex, anisotropic version of Alexandrov theorem holds. So this is substitute of sphere. What is crystalline mean curvature? Of course, if gamma 0 is equal to 1, this is nothing but area of gamma, and h gamma is a mean curvature. But in this case, of course, gamma p is mod p. In general, gamma may not be convex nor smooth, but we say gamma 0 is crystalline if gamma is convex and piecewise linear. Anisotropic mean curvature h gamma is a crystalline mean curvature if gamma is crystalline. So the key is this is a gamma, homogeneous of gamma is crystalline, is convex but piecewise linear. Okay. And so the level set of one level, sub-level set of gamma is often called Frank diagram. And double Wolf shape is, you may understood something like polar of F gamma. So this is a Frank diagram. So this is gamma. Gamma is piecewise linear function. Its level set is something like this here. But then the polar Wolf shape is dual here. So, okay. So what is the flow? Flow is just a grade, H gamma depend. Velocity is equals to something depending upon normal at H gamma. So this is a example of anisotropic curvature flow. Crystalline marine curvature flow is, of course, H gamma is crystalline flow. So there are a few examples I just write. Yeah. And why such kind of thing interesting? Just some I take from physical literature. This is the shape of crystal. And if the temperature of the material is very, very low, this is facet. And this corresponds to shape, facet of U shape. And of course, if the temperature, okay, this is a mixture of curved part and flat part. So this is a crystal of silver selenide. A lot of facet appears. Okay, so this is helium. So anyhow. Now this is a snow crystal. Okay. So the fundamental problem in analysis is considered crystalline mean curvature flow. For example, V is equal to H gamma. That's the initial value problem admits unique solution for Rn. So for a given closed surface, there a unique family gamma T so 1. The second question is this solution, if it exists, approximable by smoothed anisotropic mean curvature flow. If interface energy gamma is approximated by gamma epsilon, does the corresponding solution, gamma T epsilon, approximate this solution? This is important because otherwise you can say all solution is just a standing solution or anything you like. But this is a very good criteria whether your solution is a natural solution or not. And known result, let me say the known result is that if this problem is well studied, if in the planar motion, the curve evolution, in the case of curve evolution, okay, and this Angel, Gatti, and Taylor restricted your class of solution, class of evolving curve by what is called admissible polygon, but this is a very restricted class, but we are able to extend level set method for this kind of two-dimensional problem in 2001. However, dimensional case, even local existence was not known unless initial data is convex. A unique existence of global flow provided initial data is convex. So this is a 2006. And of course, nowadays, it's as I explained, it's much more things are available. So level set flow is a general notion of curvature flow equation which allows topological change of the flow. We consider level set equation for anisotropic curvature flow. A level set solution regarded as a level set flow. So let's recall the mean curvature flow. Its level set equation is of the flow, this type of flow. We consider this equation in Rn cross 0, not only on gamma. So this equation says each level set moves by V is equal to H. Each level. Fortunately, the initial value problem uniquely solvable in the sense of this situation with uniformly continuous initial data. Then moreover, this gamma T zero level set is uniquely determined by zero level set of initial data. Does not depend upon choice of defining function. This is introduced by Osha and Session for numerical analysis, and after that analysis established. Okay, the main result in this direction is our paper 2016-2018. For a given initial data with its boundary gamma 0, there exists a global level set for D for crystalline mean curvature flow equation. level set equation for V is something like this type of equation. Right. You also notice here's some good stuff, by the way. And this is also stable in some sense. Suppose that gamma epsilon be a smooth convex interface energy density approximate gamma uniformly. Then the level set for the epsilon combines to D in the Hausdorff distance sense in the space of time, provided that no fattening occurs. I did not explain fattening. Fattening means, fattening means if you consider even mean curvature, or if you consider such kind of shape, cross, then maybe I should write this way. This initial data, then there might be happen in approximation looks like this one, evolve like this one, but out approximation evolving something in a different way. So maybe it's better to start figure. So that's what two way to evolve. This one way and this is two way, and two way. And in the reverse approach, even if initially the zero level set is just cross, immediately this is called fattening. So in this case, convergence result is problematical because solutions may not be unique. It's unique in the sense of this level defining function, level set flow, but if it's happening, if you talk about surface, then it may have a problem. So we just put such kind of equation. This result is already published 2016 for the dimension 3. And for general dimension, this is in communication pure and applied math in 2018 with Robert Požár. And I don't say recent, but a few years ago, there's a very nice work by Chambord and Morini and Ponzione, 2017, 2019. And they studied the problem with just this. Ours are quite general, but they studied very strong. But the idea, what is the result is their initial set is arbitrary. So, and crystalline stuff is, we are talking about gamma is just crystalline, but here is a very general gamma. So gamma includes curved part and piece linear part. No assumption other than the convexity. This is great. No boundaries of D0, no restriction of space dimension. This is great. And the very more recent, Novara extend this beta is convex and F is given, even with this one. But disadvantage is the equation can be handled in a linear in kappa gamma with convex coefficient. The idea is interesting. If D is a super solution, then one expects that the anisotropic distance D fulfills such kind of equation. And this looks like linear equation, so it's great. And we have to define the correct notion of what time is up, maybe. So, time is up. Comparison principle. So to do that, we have to define correct notion of viscosity solution and conclude that if initial data this comparison principle holds. We define anisotropic non-local curvature to compare. We also need approximation by smoother facet. And of course, viscosity theory has been established a long time ago for two-dimensional case, so curve evolution. And minimal divergence is constant for curve evolution, but may not be constant in surface evolution. This is a difficulty. The breakthrough is by Norbert Požár with me and Yoshikazu Giga, my wife. And this is for this equation. Extension for inhomogeneous driving force with Lipschitz G. This is exactly paper which just published. And having G is problematical, but we are able to overcome. And maybe we skip. So we just mentioned the I think well-posedness of the problem, but of course we know the property of solution. But this is less known. On the one-dimensional curve evolution case, it is just several works, but surface evolution only work, such kind of thing is a self-similar construction of self-similar shrinking solution of higher genius and by Norbert Požár. So we give several approaches for total variation type equation. We also apply our viscosity approach to the crystalline mean curvature flow to get global solvability in the sense of level set. And the open problems, if the equation is forced order, has no divergence structure, well posedness is often left open. Example is this is coming from crystal growth relaxation mechanism. This is actually exponential stuff, so that's problematic. Also, one harmonic map has many results for resistance, but uniqueness is widely left open. So I think it's a good time to stop. So thank you very much for listening my talk. Thank you very much.
Thank you. Thank you for a wonderful lecture. So it's let's take a few questions. Anybody have any question? You can directly ask questions to Professor Giga.
Question. I have a question to Professor Giga.
Sure.
May I put the question? May I put the question, Professor Giga?
Oh, sure. Yeah. You can directly talk to Professor Giga. Yeah.
Screen disappear. So.
Okay. I enjoy very much your talk.
Thank you very much. Rodriguez. Hi.
My question concerns the total Fourier flow in presence of an obstacle. If you have an obstacle for the total variation flow, can you still use this approach? Do you have any?
I think if it's a variation, okay, it depends upon equation. If the equation has a variational structure, like usual obstacle problem, I think it's possible. But what kind of obstacle? Just the obstacle of value, obstacle of function. For example, the u is greater than some psi or something. Is that what you mean? Yeah,
that's
I think.
May think about the crystal growth against some plants.
Yeah, this is another story, I think. Let's see. I lost the pen. Yeah, this is another story. My answer is if it's for example, if your problem is something like with u is less than psi, such kind of obstacle is I think no problem. But what you say is if you host some body and you have a crystal surface, and this is move something like this. This is what you mean, Jose? Professor Rodriguez?
On the situation, of course, the classical obstacle is psi. I mean, the classical obstacle problem with u larger or equal than psi, but you can also have the level surface approach, where of course you must define obstacle in a different way.
Yeah. But you are talking about surface evolution with obstacle. This is an interesting topic. So you have some stuff, and this is a crystal surface, and trying to move this way. And this is another story. But if it's obstacle, this is that it looks like tangent. So
okay.
Yeah. So,
any other questions? Or?
Yeah.
Anybody? Then let me ask a question. You mentioned this the computational issue. I mean, result by the Usher. I mean, method by the Usher and Sessian.
Yeah.
For the mean curvature flow.
Yeah.
And can you add some comment on that? I mean, some other method or other than the level set method for the computation?
Thank you very much. I skip everything. So Let's see, you are talking about
computations.
Computation. Yes, sure. Yes. Okay.
This is
of course,
the famous numeric.
There's many way to compute. Okay.
Mm-hmm.
Even if you look this level set flow equation, there's many way, like for example, Duke, something like using finite element method, you can. But of course, for mean curvature flow equation itself, there's many way to calculate numerically. For example, using phase field or Allen-Kahn equation. So there's many ways to approximate Allen-Kahn equation by approximation by Allen-Kahn equation, or we have some threshold approximation. For example, if you this is also proposed by Osha, Benman, Osha, and Merriman, Osha scheme. There's also this Merriman, Osha scheme is something that first we solve heat equation with whose initial data is a characteristic function of the crystal shape, and then solve heat equation, and then with very small time, we just chop this of course the sub-level set of this solution with level half, something like that. And then we take this set as the initial data to solve something like that kind of threshold method. Is another typical method to solve the problem. So So there are many ways to solve.
Okay.
I just mentioned the ocean session original level set method. But numerically, there's a lot of methods. Of course, if you are interested in only the evolution of smooth in curvature flow, you have, of course, particle tracking method and many methods, numerical methods. And yes, so, and sometimes crystalline stuff can be also another way to calculate. By the way, the level set crystalline flow can be also calculated numerically. And this is a work by Takei and Osha and Obermann, and there's 4 authors paper which I don't remember exactly, by using let's see, by using
okay, that's good enough. Let's take just one more question, quick question, if there is any. Audiences, any other question or? Okay, otherwise, thank you very much for wonderful lecture, Professor Giga.
Thank you very much for listening.
Very happy to see you again. Okay.
Thank you.
Thanks a lot, everybody.
Thank you. So good night, good evening, good morning.
Yeah, good night, Ian.
Thanks a lot. Good night, everybody in Asia.
Yeah, good night, everybody. Yeah.
Bye-bye. Thanks a lot.